Does anybody have any questions? Now that I've unmuted myself, does anybody have any questions about anything? All right. So I'll take your silence as everything is kosher. And put the chat screen up. Okay. So we're going to finish off chapter 20 today, and I think next week we'll do chapter 21. I think I'll have extra time at the end of class today. So actually, you guys seemed excited when I was talking about my experiences in Hungary. So I brought some artifacts. So some Soviet and Hungarian artifacts, well, actually Nazi as well. So from papers from the Third Reich I picked up on Europe. So if I can show those after I'm done talking about chemistry. Okay, so this is where we left off, is talking about batteries, and the more common ones that we see today. We have the alkaline batteries, similar to a dry cell, but they have potassium hydroxide in the middle. And basically, the battery has zinc on the inside coated, and it's usually the anode. The anode is the one that corrodes away for these batteries. And if you remember also from the Nernst equation, the non-standard, as the battery is discharging, it's going to steadily lose its electromotive force. So, and then it talked about a lead acid battery, and a caution, word of caution, be very careful when you when you work with lead acid batteries in your car. I recommend safety glasses because there's sulfuric acid in them, and those will blind you and scar you very quickly. So, and what's nice about lead acid batteries though is they're very, very easily rechargeable, and they're very, very robust. So, and I mean, like the other batteries, like lithium-ion batteries, they are not nearly as robust as a lead acid battery. Because I mean, well, among other things, the components in there, it's just there isn't as much room for issues like overcharging that you get with a lithium ion. So and here's a lithium ion battery, and how a lithium ion battery works is that lithium ions transport. They go from graphite, so you have lithium ions trapped in a graphite matrix, just like, I mean, graphite, it's a hexagon, and there's sheets of it on top of each other. So sheets of graphite, and the lithium ions are in between the sheets of graphite. And when the battery discharges, the positive ions goes towards the cathode. It goes towards a usually transition metal. So it's like, iron, vanadium, that kind of stuff. I'm not sure which transition metal they use for lithium ion batteries, but it's usually transition metal oxide. And the ions move in that direction. And as the lithium ions move in that direction, current flows. So, well, this is one of the few times you could argue that the current actually is positively charged is moving, but the electrons move. The positive ions, the positive ions moving this way cause negative ions to move. Well, I guess no, they're going to follow. They're going to follow as well. So the negative ions will also follow, and it induces the EMF, the electromotive force in the wire, and it causes. Then you can do work on the electrons as you use the push the electromotive force across the wire. So lithium ions are nice. They're great batteries. Lithium is a light. It's a light. It's a very light metal. Really tiny ion, and so that means tiny battery that has lots of electricity in it. So there's a couple issues. Well, so how do batteries go bad? So lithium ion, and since we use them so much, how they go bad. One of the biggest problems is what's going on here. The interstitial, like the fluid that's in between the graphite and the metal oxide, the transition metal oxide. And it's difficult to get the lithium ions to move through it. So, one of the more common mistakes is that you overcharge the battery. So when you overcharge the battery, you push, well, when you recharge the battery, what are you doing? The lithium ions, they move to the other side. And so you get the lithium ions here between the and the graphite. And graphite conducts electricity. Graphite, that's one of the interesting things about graphite, it conducts. And if you charge the battery past the lithium ions, what happens is that the lithium ions turn into lithium metal. So it turns into lithium metal, like zero. I'm saying it turns into lithium metal. And lithium metal is an alkali metal. It's very reactive. So what the lithium metal does is it'll then react with a carbon, or usually more frequently, it reacts with this interstitial fluid. And when that happens, it just damages stuff. So, then just over time with that repeated damage, the battery just doesn't work anymore, or just doesn't hold charge as quickly. Because so if the interstitial fluid, for instance, is damaged, it's just harder to transport lithium ions across the between the anode and cathode, between the graphite and the transition metal oxide. So and I mean, if you damage all the graphite too much, the battery just doesn't work at all. So so that's a precaution for lithium ions. You don't want to overcharge them. So I try to be as cognizant of that. Once I learned about that, I found that my cell phones and my laptops survive longer. So there are certain times that I charge the heck out of my electronics. Even right now, my iPad, I'm using it for teaching. It's 79% battery. Or can you see it up there? I guess you can. Something you might notice is that when I come to class, it's almost never at 100%, because I don't want to overcharge. I mean, this is a pretty old. Let me think how old this is. 5 or 6 years old. So I mean, the battery is still going south, but I mean, it's still holding up pretty well. One of the secrets, like I said, is just not to overcharge it. I will overcharge it when I go on an airplane. Like if I'm going to have an 8-hour flight, I like my Netflix, so I will take the little bit of a risk and overcharge it to so I can get that extra 30 minutes of watching Netflix out of the iPad. But I mean, like cell phones, I mean, unless you're gonna go like on a long hike that you're not gonna be around like to recharge, I mean, charging to 80-90% is fine. I mean, like it's just be careful when you get in the high 90s and the 100%, then you can start be doing the damage. I mean, it still does, like inadvertently you still turn some of the lithium ions into lithium metal. So I mean, the battery just degrades over time. So I mean, that's the primary cause of that. Other things are just like corrosion, kind of thing. I mean, not within the battery itself, but like in the wires and the leads and that kind of stuff. I mean, that's other things that can happen. You get just corrosion on there. And so what else? So lithium. I guess that's about it. How are we doing? Any questions with lithium ion batteries? Nope. Okay. So, but I mean, we use them so much. And another thing I should mention, batteries though, when it comes to stored energy, batteries are great. But if you really, really need to have energy, the thing that has more energy than batteries is fuel. So fuel has significantly more energy. I mean, if you're wondering why you know why don't we have airplanes that run off of batteries? I mean, we have drones, right? You know, why don't we just start having electrical propeller planes? And the reason for that is because fuel just has more energy and it takes you further. So I mean, you could feasibly, I mean, a Tesla has like what a range of like 200 miles, but I mean, you know, a decently sized car has, you know, with a full tank of gasoline has a range of 400 to 500 miles, right? So why is it that the gasoline has more range? Because there's more energy in fuel than there are in batteries. But there are nice things. I mean, but I mean, you know, I'm not going to run this cell phone off of a internal combustion engine. Can you imagine that? You know, I'm like, you know, like a lawnmower. I'm like, you know, pulling it to start the engine and have to pour in fuel to the cell phone. I mean, of course, electric is way more convenient, and you know, doesn't have sound, doesn't give emissions. So I mean, there are a lot of advantages over electric, and then versus, you know, everything running off of fuel. That would be an interesting, you know, world, right? Everything runs off of fuel. Okay, so another thing are fuel cells. So fuel cells are very efficient. I mean, so as I mentioned, fuel has a lot of energy in it. So a lot of calories, a lot of enthalpy in a fuel cell, and in fuel in general. And the fuel cells that we use today, well, at least for applications that involve locomotion and energy, is a hydrogen fuel cell. And this is old technology. So this technology goes back to the Apollo moon program. So the Apollo spacecraft and the space shuttle, they both ran off of batteries and fuel cells. So with a fuel cell, what's happening is you have the anode is, for our fuel cells here in the United States, well, I guess pretty much everywhere, at least for the Apollo program and the space program, the anode was hydrogen. So hydrogen goes, and then there's a chemical reaction takes place. The electrons leave hydrogen, they flow towards the cathode, and then here oxygen then goes from oxygen 0 to oxygen -2. So the chemical reaction that happens, instead of the electrons just bouncing back and forth between the atoms, the electrons flow through a wire and are transported. So not in the textbook, the fuel cells, they're a really difficult technology, and they're expensive. They're expensive because typically the surfaces of these are usually platinum. So the anode and the cathode, they have platinum in them. And so, and strips of platinum work really well for this. Of course, platinum is more expensive than gold, right? So that's why they're so expensive, is because of the platinum that's in there. But what's going on though is a hydrogen comes in contact with the platinum, and then on the platinum surface, the hydrogens attach. And platinum is a metal, so the electrons, you know, can flow. So platinum, the platinum metal, it's the electron, you know, this is, you know, platinum is a piece of metal. It conducts electricity just like anything else. Actually, platinum conducts electricity very well. And, you know, it's a good conductor, electrons flow. And now the hydrogens, they leave the platinum and they form, you know, hydrogen ions or you know, H3O plus or whatever. I mean, whatever it is you look at. And then also on the other side, so electrons coming down the other side, you have oxygen, and the oxygen breaks apart. So same idea, new piece of platinum. You have the oxygen comes down, the electrons come to the oxygen, and O-2 pops off, right? So, and then here in the interstitial medium, then the acid and base forms water. Basically, there's an acid-base neutralization reaction that happens in there and forms water. And so how do you make this cheaper? Because platinum is expensive. You can use something like we use in the catalytic converter. You can have a zeolite, some sort of metal oxide, kind of, non-platinum metal, and you put like nanoparticles of platinum on there. But now that's a difficult thing with nanoparticles, because you have something like a zeolite that's now an insulator, and so you're using an insulator connected to an electrical circuit. So that's have some issues. And then also just the transport, you have hydrogen atoms and they're transporting through an oxide layer to nanoparticles. So it's not a strip of platinum, it's now islands of nanoparticles. And you have all these ions that have to transport through all these different media. And it's difficult. I mean, to do it, there's a lot of things that can go wrong. It doesn't work as well. And I mean, it's cheaper, but it's difficult, like I said. And so now what? So what? Fuel cells are things that only rich people have. So I remember I was in grad school and Arnold Schwarzenegger was the governor of California, and he goes like, I care about the environment. I'm going to turn my Humvee into with a fuel cell. I was just like, thanks, Arnold. Thanks for flexing me, that with all your money that you have, like I've got my bus pass, So because only, someone like Arnold Schwarzenegger could afford, and NASA uses it. NASA and Arnold Schwarzenegger are the ones that can afford fuel cells because they're so expensive. I mean, it'd be nice. If we can get fuel cells to work and they work really well for hydrogen, but I mean, look at the issue with hydrogen. You're breaking apart hydrogen on a piece of platinum. What about something else? I mean, what about like if you have an octane, like, a C8, like an octane hydrocarbon. And now what else is going to be going on? Well, you're going to be forming little bits of carbon and carbon something hydrogens, and they're going to be floating all around. It's going to be a chemistry nightmare. So the fuel cell molecules, we try to make them simple. When you do these, you look for really simple molecules like methanol, hydrogen, ethanol, and so the molecules that we use for fuel cells are typically very simple. And coming up, a breathalyzer is a fuel cell, looking at ethanol. But one more thing about these fuel cells, hydrogen oxygen fuel cells. This is how NASA like to do a lot of redundant systems and efficiency. They didn't rocket up pretty much any water with their astronauts. The astronauts drank the water from the fuel cell. So their dehydrated food and their drinking water, all this stuff came from the fuel cell. And man, that's a tough job. I mean, like our astronauts, go to work in the morning, you got to go in you have to go in a rocket, which is like, a slow exploding bomb, and some of them do explode. And then when you get to space or whatever, wherever you're going, you gotta wait for your fuel cell to spit out water, so you can either have a drink or have a some of the whatever dehydrated whatever food you have that's with you on the spacecraft. So man, it's a tough job. I'd love to be an astronaut. That's one of my dream jobs, but I don't think I could. So well, the nice thing is actually astronauts, on the right age, they like old astronauts, people in their 30s and 40s typically, or even 30s. 30s is a young astronaut. They like old people. So, well, it depends on your definition of old. They don't want anyone young and headstrong. They want old, cautious people. So, and they like PhDs, especially in physical sciences and engineering. So that's another score for me. But I don't like confined spaces. That would be a pretty big strike. So I don't know. Who knows? Maybe they'll put me. Maybe they would recruit me just so they can mess with me. Who knows? So if you're listening, NASA, I'm in. So, but no, I don't know. Probably not. That would be. But they like to work out. That's one thing. Also, astronauts, they work out a lot. And I'm too heavy though. I mean, you could get a smaller, thinner astronaut and get more fuel and other kind of equipment versus me. Okay, so fuel cells. What else do we use fuel cells besides, you know, rich people's cars and NASA spacecraft? Breathalyzer. So a breathalyzer is a fuel cell, and I've actually never used one, so I don't know. I've never used a breathalyzer, and I've never had fortunately, I've never had a circumstance where I've you know, been asked to or had to or whatever for whatever reason. And the way that they work is the amount of ethanol vapor that's in your breath. They can calibrate that, and I guess they back calibrate it to your blood oxygen level, but blood alcohol level. But I mean, I've never been arrested in general, and certainly not for drunk driving or anything like that. But I think they take you to a hospital and they draw your blood or look at your urine or something. I don't know. I'm not sure. But if you're wondering how a breathalyzer works, it's a fuel cell. And we only can get it to work in small things, and we haven't been able to mass produce it, or scale it up to something that's very usable. And it would be wonderful if we could, because they're very efficient. A fuel cell is on the order of 60% efficiency. So like a gasoline engine is on the order of 20% efficient, meaning you haven't studied, you can study later about the Carnot cycle, and meaning if you have 100 joules of energy, you get 20 joules of work from a fuel cell. I'm sorry, from a regular internal combustion engine. Diesel is a little more efficient, maybe on the order of 25%, depending on how good it is. But then a hybrid car, that's on the order of 1/3. But a fuel cell is on the order of 60-ish%. So you can triple your efficiency using a fuel cell. So, I mean, that'd be nice, right? So if you, rather than having 25 miles a gallon, you get 75. You know, that'd be wonderful. You know, kind of thing. So versus and you know, so I guess it's probably closer to 50-ish. You know, for a hybrid car. I don't have a hybrid car. I've rented one before. Well, they gave me one. I just, you know, said any car, and they gave me a Prius. So actually, I don't like Priuses. They're too flimsy. They're so light. I guess I like the solid steel. So, but because Priuses don't have steel frames, they have either aluminum or magnesium. I think it's magnesium. It's very light. But anyways, they are efficient, but they're flimsy. But so, have any questions? Do you have a question? The fuel, what would a fuel cell look like? So the question is, what does a fuel cell look like? So I mean, you can see here with a breathalyzer, the fuel cell itself is a box. And so what the Apollo fuel cells look like, they look like kind of like lead acid batteries, except they were kind of painted gray. So they're just the box. It's like a box, and then you have the inlet for, I mean, you have tubes that you attach to it. You have one tube for the hydrogen, one tube for the oxygen, and then you would have the water outlet, because that's what they probably something, I don't know what the what they use to filter out the electrolytes, because this is inside the fuel cells. is electrolytes. So I'm assuming there would be some sort of, I would guess, a semi-permeable membrane and kind of something like osmotic pressure or something like that. You can get water out. You have a question? Yeah. Yeah. So question is, when they start the fuel cell, do you need to have water? Yes, you need to have something to transport, and electrolytes are very common. So you do have, because without the aqueous solution, you wouldn't have the salt bridge equivalent. You need to have the ions transport. So you need to find a way to transport the ions. Unless there's some new fuel cell technology, I'm only familiar with the older technology, unless there's something new. But you need something. You need something to let ions transfer, and it's almost always aqueous, right? And so that's very common. So is that what you mean by what does one look like? It's just it's a box. I mean, yeah, they do. They need to have water so that like I said, so the ions can transport. Yeah, and what one would look like using fuel instead of hydrogen and a gas, you would have just a fuel tank or fuel line that would put it in through there. So in the case of a breathalyzer, the fuel line is the 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 breath of the suspected drunk driver. So does that answer your question? Yeah, and then just I'm waiting and I'm repeating the question because of the Zoom people, and also the people that listen online, so they know what. If you're wondering why I have odd social behaviors with my, I guess people are used to my odd social behaviors in general, but with the questions, no, you're welcome to ask questions, but that's one of the complaints I got from at least the people there. So repeat the question. Okay, so what else can you do with batteries? And one of them is hydrolysis. Electrolysis. Electrolysis. And so if you take just something in water, just plain old H2O water, and you connect an apparatus like this where you have an anode and a cathode. I know you have it hooked up to the positive, but the anode is the water. You hook it up here, and then you have in a solution here. You see this is all connected in the water, and you have something. You can even do this with pencils because graphite conducts electricity. But you can have a conductor here for the anode and the cathode. Hook it up to the opposite ends of the battery, and then you want something to collect the gas, like so. And if you do this, you get electrolysis, and at the anode you get oxygen. So this end you make O2, and on the other end you make hydrogen. And at first guess is like, oh, is this how we get hydrogen? The answer is no. The way that we normally get hydrogen, at least for industrial settings, there's two main ways. One of them is known as steam reforming. So you take methane gas, natural gas, and you react with water, and that forms hydrogen. The other place that we get a lot of hydrogen is in a petroleum refinery. So when you reform molecules, so meaning if you have a straight chain hydrocarbon and you reform it into something like toluene or something like that, or xylene, then when you hook the hydrocarbon up and you reform it, it forms the cyclized compound, plus it makes hydrogen. So hydrogen pops off from when you cyclize the carbon. So that's the other primary source of hydrogen. If you want hydrogen, this is typically how you do it, though. If you have a chemical plant and you say like, all right, this process needs hydrogen, I need to generate my own hydrogen, it's usually done via steam reforming. And like I said, the other place you get lots of hydrogen is in petroleum refinery. And one of the issues here in the United States is that we have 50 states and we have 50 different formulations for gasoline. So each state has its own formulation. And one of the byproducts of certain states and refineries is hydrogen. So actually, we don't typically get hydrogen this way, but we do use electrolysis to make oxygen. Can anyone think of a circumstance where you have lots of water, but you would really like to have oxygen? Not space. Think down. Yes, ocean. And what is something, what type of vessel doesn't see air very much? Yep. It's how subs get in a nuclear sub at that. So nuclear subs, I mean, a diesel powered sub, it needs to go to the surface and recharge. Nuclear submarines, they need to, their sailors need to breathe. So this is how they get oxygen. Question? Oh yeah, works just fine. Yeah, salt water works fine. Actually, it's going to be easy. It's going to be more conductive. If you have ions, it'll conduct electricity more quickly. So yes, salt water works just as well and as fresh water. So, but I think it would work better. If you're wondering what happens in the sub, though, they dump the hydrogen. The oxygen they keep inside of the vessel, but because it's separated, you have the electrolysis separated. They just take the hydrogen, they just drop it off the side of the vessel, and it typically dissolves in the ocean. So, this could be a way. We have looked at using electrolysis. So there's certain types of energy like wind that's just not very good. Like because I remember I showed you the wind energy. It's not consistent. So wind energy is not consistent. So maybe what you could do with that energy instead is to do electrolysis and make hydrogen, and then have a bunch of hydrogen and then run the hydrogen off of gas turbines. So that's another idea. So that's a possible future for this. It's been talked about. So other questions? Okay. Another interesting thing are electroplating. So there's a couple ways you can electroplate things, or even like not even, well, this is how you properly electroplate. But if you want to coat something with noble metals, one of them is you can just stick them in a solution. So if you want, you can buy these kits at home. Like, let's say I'm just really good at making things out of tin. Like, I want to make something out of tin, and I make I don't know, a toy soldier. I have a toy soldier, that I made out of tin, and I want this to be a golden soldier. So what do? I can then take the tin soldier and put it in a solution that has gold ions, and then the gold ions are going to react, and it's just on the surface, it's just going to coat that soldier with gold. That's one option. When you do that, though, it's not very even. It gets kind of fluffy. Like it's like, there's kind of flaky and fluffy, and I mean, it works, but it doesn't work very well, kind of thing. So, but yeah, you can do that at home, and just be careful though, because if you do those ions, make sure you use safety glasses. I have a couple pairs of safety glasses at my home. So just make sure you wear safety glasses if you do that, because the ion is going to be very caustic. But you can use a electroplating, and this is how you get cheap jewelry. Like, have you ever gone to the store and you see like there's a pair of gold earrings for like $20, or you can buy gold rings for about the same price? So you go to a store and like, okay, well, here's some gold or gold plated, something that you can say gold plated or gold or something, and it's really cheap. It's something that's under $100, or you go to a jewelry store and you say like, oh yeah, here's some earrings, and they're like $5,000, with the diamonds, besides the diamonds, or you have really, really expensive other things, it's like, well, I mean, what's the difference? And so like for earrings though, a lot of times, so if you have your earrings, or if a ring, maybe it's easier with a ring, you have the whatever, the jewel that's there. If you look inside the setting, like if you have the, you have the setting kind of thing and on the ring, if you look inside there, that's actually usually where they attach a wire. So when they make the gold ring or earring, like they'll put a wire in there, and then they'll stick them into an electroplater. So it can be any material. And in this way, I mean, written here, it's silver, but it could be gold, it could be platinum, it could be nickel, and chromium are also common. So for cars, but what you do is you put the noble metal, and then on there you have a solution. So you have a solution with the metals in it, and then you have whatever it is you want to be plated, and you attach a wire to it, and then you turn on the current, and then the noble metal loses ions, and then the noble metal, noble meaning not reactive, it then electroplates on the surface. And unlike the home kits where you just let it sit in there, it gives a thicker layer. It gives a much thicker layer, and it's not going to be as flaky. So it's not going to be flaky like you do with the solutions alone. So, and well, we're going to do some calculations on this, but this is very common for jewelry. And like I said, one of the tricks though is to put the where you electroplate it somewhere where you wouldn't really notice it, like behind the jewel, or also like, I mean, earrings a lot of times have the fasteners. So you would do something like have electroplate this, but then make your fastener out of brass or something like that looks like gold anyways, and just kind of weld it in, or whatever, solder it in or something like that. And so it looks like it's attached. So that's how they make those, like I said, cheap earrings. What they do for you see a lot of trucks. I guess we don't have a lot of trucks here in Hawaii, but if you go to the mainland and some of those truckers, they have like these really shiny, beautiful chromed trucks. And our technology has changed. Back in the day when when regular cars had shiny chromed things, a lot of times they would do side corrosion. So you would have your chrome bumper, but then over time it would just get flaky and you would get pieces of the chrome falling off. How we've gotten around that is when you chrome plate something now, you actually put a thick layer of nickel on it, and then chromium, and the nickel layer prevents I mean, you can get pitting. I mean, you run into a bug fast enough and you're driving 60 miles an hour, and you have a little bug hits your bumper. I mean, it can, it's gonna, if you could pierce the metal, or you run into a bird. I mean, like the beaks are pretty tough, right? You could pierce the metal. Now if it pierces through to a nickel layer, nickel layer will protect it. It won't cause the side corrosion where you get the flaky stuff coming off. So that's how it's different now. But let's go back to this electroplating and let's do some calculations on that. So when you do this, so let's say if you want to gold plate something. So let's say I want to gold plate. I've got my ring. I lose my wedding ring. Actually, my wedding ring's platinum, but let's say I lose my ring and I don't have the money to replace it. What if I run to the store and buy a gold-plated ring? You know, how do I make this gold-plated ring? So what mass in gold in grams is plated by a 25-minute flow of a 5.5 amp current? So what's nice about this is we use dimensional analysis. Oh, I forgot to say something. A lot of these things, these electroplaters, they use, this is old technology. And I mean, we don't use this as a construction material as much in industry, but one of the things that you use when you mount the things to electroplate, they actually use wood. So if you're wondering what they use use wood very frequently, but wood and also PVCs can be used as well. But you have to be very careful about what you put, when you put stuff in here. If you make it out of metal, it's going to electroplate, right? So you typically mount these, and like the wires, you know, wires typically, like, because you still have to run the currents. I mean, but usually you coat wires in nylon anyways. So it's just whatever metal you have exposed, it's going to turn into gold or silver or whatever it is. So a lot of times, like I said, you use wood. Okay, so this problem here. So we have we're using this reaction, gold plus 3 ions plus 3 electrons makes gold metal. So what mass of gold in grams is plated by a 25-minute flow of a 5.5 amp circuit? So this is nice because you can remember good old dimensional analysis from chemistry 161. So you just do units. 5.5, an amp is a coulomb per second. So 5.5 coulombs per second. Actually, maybe I'll start. You know what? Maybe I need to make it neat. I want to make it pretty for you guys. I'll start with 25 minutes, 60 seconds per minute, and then 5.5 coulombs per second. So notice that I'm trying to set it up so we can do dimensional analysis. So how do we go from charge to something? You can use Faraday's constant, where it is 96,485 coulombs per mole electron. So this is where you would throw in Faraday's constant. And now we gotta look at the stoichiometry. There is a mole of gold to 3 moles electrons. And now you gotta look at the atomic mass of gold. And gold is 197. 197 grams gold per mole gold. I guess I made my line too long. I don't think I'm missing anything. Okay, and if you do that, if you do this, you get 5.6 grams of gold. And notice the units though, right? The fun stuff in 161. Minutes cancel, seconds cancel, coulombs cancel, moles, electrons cancel, moles of gold cancels, and we're left with grams of gold. So, but that's how you do it. And the step that mucks everyone up is that one right there. The Faraday's constant. Do I divide it? Do I multiply it? Where do I fit it in? This is just, you know, keep look at the units and make sure they're done properly, and you do that, of course, it tends to work really well. So recap for this one. We have mass of gold. We're running this thing for 25 minutes at a current of 5.5 amps. How much gold am I going to electroplate on this thing? And you can solve it by dimensional analysis. And I made sure if you notice when I started off by putting 5.5 coulombs per second. I mean, if you do that, then you would have 25 minutes, 60 seconds per minute. It would still work, but it wouldn't be as pretty. So that's why I recapped, I returned. I was like, I'm gonna try and make it prettier. I mean, it all works out mathematically, but just look at it and try and go from left to right with the units. So, questions on this? And I mean, if you think about it, though, 25 minutes for 5 grams of gold, that's a long time. So you gotta put these things in the to electroplate them. It take a while, on the order of hours to get a sizable amount of some whatever it is you're putting on there. So what if you're putting nickel or chrome? So the cheap jewelry though, I mean, what's nice about gold is it's got a color and it's kind of pretty, and I mean, other things you can silver plate. You can silver plate silverware. That's another thing you can silver plate, kind of thing. But you can usually tell the silver plated silverware because, I mean, it rubs off, kind of thing. So versus like the pure sterling silverware. But the idea though is if you're cheap, you not buying the solid things, and it's going to be a little bit of an issue that'll just kind of flake off and fall apart. So other things we can do, if you wondered how we get bleach. So how we used to get bleach, there's an old way of getting bleach. You would take sodium chloride liquid. You can melt salt and then stick in, an anode. So like an anode and a cathode, you can hook it up to a source of power, and on one end you will grow sodium metal, and the other end you'll make chlorine gas. So if you wondered how we get metals like sodium, lithium, potassium metals, a common way to do it is that we take the salt and we melt it, and then we do electrolysis to it, so to grow the metal. And what they used to do for bleach is you bubble off the chlorine, you put the chlorine through water, and then you would throw the sodium metal into the chlorinated water, and you would make bleach. Or you could use the chlorine to do like purify water and use the sodium for something else. So throw it in the water to make sodium hydroxide caustic lye. So nowadays though, it's a lot cheaper. You can use an inert. Oh, and you mentioned about what to do about the salt water. Oh, I guess I have to backtrack and say you gotta be careful with that, because you can make, I guess you would have to purify the water, because otherwise you would get chlorine. So, I'm not sure if that would, I guess this is true. I'm sorry, I'm gonna have to backtrack on myself and say that if you have salt water in there, you'll make chlorine gas or whatever the halogen is. So doing this, you can make, was like I said, common to make bleach and to purify water. So last topic is corrosion. Corrosion is a multi-billion-dollar problem, billion with a B, maybe even trillion with a T, dollar problem, and especially with iron. So corrosion just wrecks things, especially things that are made of iron. And corrosion is an electrochemical reaction. The anode is the metal, the iron, typically, because when you say corrosion, we almost always mean iron, but it can be anything. So the metallic iron is the anode, and the anode corrodes, and the cathode actually is the rust. The cathode grows. And what happens is, for iron, it needs to be wet. You have oxygen dissolves in water, and then through an electrochemical reaction, rust is formed, and rust grows, and the iron is corroded away. So now that we know what corrosion is, how do we prevent corrosion? And one of the easiest ways to prevent corrosion is to keep it dry. If there's no water, that's the equivalent of removing the salt bridge in the battery. There's nowhere for the ions and the electrons to transport. So that gets rid of that problem. Keep it dry. Another one is a sacrificial anode. So what you can do is you can connect something to a big block of zinc is typically done. A big block, so something that's more reactive. And that's known as a sacrificial anode. And they do this with the big iron pipelines. So, well, before that, does anybody know the difference between a pipe and a tube? Pipes are welded, tubes are extruded. So I remember when I was a kid, they had like Play-Doh, and then you could make spaghetti out of it. You could take the Play-Doh and you could push it and squirt out like these like Play-Doh spaghetti things. That's called extrusion. Tubes are extruded, meaning you have something, you have metal, you have polyethylene, you have nylon, and the same idea. You have this liquid and you have this just like this hole, and you push on it and you extrude out the tube. So that's a tube. A pipe though is welded, meaning you take a flat sheet of something and have you ever seen the inside of like a toilet paper? Like it has like these pieces of cardboard and they're wrapped around each other and glued. Same idea for a pipe. So a pipe, you take a piece of iron, a flat sheet of iron, and then you weld it. You weld it and you continue to weld it to form a pipe. So although we use pipe and tubes interchangeably. So if you wondered, how do we make these huge pipelines, and why do we call them pipelines and not tube lines? Because we take flat sheets of metal and then we weld them together to form pipes. But I mean, having a pipeline underground, exposed to the air, either way, it's gonna get in contact with water, and pipelines are expensive to make, and iron is a very good material for it, but it also corrodes. How do we protect the pipeline? And the answer is you connect them all up to sacrificial anodes, and they just have these huge plugs of zinc. And then every 10 years or so, you go and you just replace the slug of zinc. And as long as you keep on doing that, the iron pipe is not going to corrode. The zinc will corrode first, and the zinc will corrode as long as it's electrically connected to the iron. The zinc will corrode first, and that'll protect your iron pipes. If you wonder what galvanized steel is, so a lot of cars have galvanized steel. So galvanized just means it coated in zinc. So, and why is that? Because it prevents corrosion. As long as there's zinc there, it's not going to corrode. And the last way to prevent corrosion is something called passivity. So you can do this with iron. A lot of lingo for corrosion is with iron. The way you passivate iron is you throw it into nitric acid. And so where this came from So if you have a block of iron and you throw it into nitric acid, it forms a lot of bubbles. You throw it in there, lots of bubbles, and it stops. It's passivated. It doesn't, and what happens is that it forms a protective oxide surface layer over the surface of the iron or whatever it is you're using, and then that passivated layer protects the material. So it's not as commonly used in iron. Iron more commonly used as sacrificial anode, and what is more passivity, although it's not directly used this way, certain materials, so like aluminum and titanium. So whereas iron here, when it forms rust is really soft and flaky. Whereas aluminum and titanium, if you have a block of aluminum and or titanium, you form an oxide layer, but the oxide layer for aluminum is really tough. We give aluminum oxide. This is also known as sapphire. So a sapphire is aluminum oxide, and if you know the Mohs hardness scale, the hardest mineral is diamond. The second hardest mineral is carborundum, which is aluminum oxide, which is a sapphire. So sapphire is the second hardest natural material, at least as far as minerals that we use for the hardness scale. So the sapphire layer on aluminum is really tough, whereas the rusty iron is very fragile and flaky. So aluminum is great in that regards. So it makes that passivated layer, and it stops corroding. So we use aluminum a lot for it. And aluminum's light too. It's light, it doesn't corrode as easily. So aluminum's great. Same thing with titanium. Titanium is great for that regards. There's a couple things though. Aluminum, the chloride ion can penetrate through this passivated layer. For titanium, methanol can penetrate through the passivated layer. So it depends on your application. You very, very infrequently see aluminum used in water applications. So if you wonder why, like, oh, we use aluminum for lots of things. We use it for cars. I mean, I know we have aluminum cans for things, but I mean, they're not long. We don't think of an aluminum can as an investment though, right? We don't think, okay, I'm going to have my aluminum can. It's gonna run for 30 years like an airplane. Like, no, not really. And you don't see aluminum plumbing either. So because of chloride anion having issues with that. So you don't want to have, and you don't see many aluminum boats. And the ones you do see are typically freshwater, like canoes. You see a lot of aluminum canoes. You don't see too many aluminum, battleships. Like why are we making battleships out of steel when we can make them out of aluminum? Then we have to worry about it rusting. Like, well, because of the ocean's got chloride in it, so it'll corrode that aluminum battleship. So that's why. And propellers, they use aluminum. They use like brass. They have a specific type of Navy brass. So to make things out of the propellers they're not made of aluminum. Is my point. So you don't see aluminum as frequently in water applications because of that. So and I'm done. Anybody have any questions? Yeah, question. How does what work? How does anti-rust work? I don't know what anti-rust is. I have to look it up. according to Google, anti-rust is just like, it just coats it to prevent it from, does it get rid of the rust? You, yeah, are you talking about the RLM or something, KRM? It's a yellow bottle, something. Rust, is it this? Because if, well, you can get rid of, if you have plain old iron oxide, you can use something called a chelating agent. That'll get rid of it. That'll get rid of any metals. So we don't really talk about this semester. Chelating agent, it means claw. So you have EDTA is a very common one, ethylene diamine tetraacetate. So you have a metal ion like iron, and then you have it's going to be a 4. So yeah, the EDTA, and it kind of like a bird has its talons. Here's my bird. Here's a beak. Here's the wings. Looks like an airplane. Airplane with a I don't know, with a trident. Yeah, that's my bird. Don't pick me for Pictionary. But like the claw on a bird, you know, like when it kind of comes down and grabs something, you can have molecules that kind of claw around metal ions, and then this can go into solution. So that'll get rid of rust. So I know that there's the lime away or rust lime something. According to my quick Google search, your question about anti-rust is it coats. It's a coating, and then what happens when it coats? It's the equivalent of keeping it dry. Because then if you put your anti-rust layer on here, you've got a nice big black layer of anti-rust. And so when there's water, when water comes here, it does not come into contact with the iron. Therefore, if there's no contact with the salt bridge to the anode, then it can't corrode. So, and unless we're speaking different languages, I mean, in terms of what the products are. So I've never heard it. It's the first I've heard of it. So well, it's not me being right, it's Google being right. And none of us are as smart as the Google. Well, in terms of trivia, reasoning, we're still superior to anything. So other questions? Okay, so I wanted to, and I'll show you, you can touch them, but let me actually I'll stop recording.